Hello students, welcome to Educate. In previous lecture, we have studied about Bernoulli's theorem. Now we are going to see Toricelli's law and other related facts. So in case of Toricelli's law, here we consider this is a container having certain liquid in it, and this is small orifice through which liquid is flowing out with velocity v1. Here area of cross section is a1. Here at the open surface area of cross section is a2. So Toricelli's law, the speed of efflux v1, here our concern is to find out the speed of efflux. Efflux means liquid coming out from the side of the container is given by the application of Bernoulli's equation. If the container is open at the top to the atmosphere, then V1 will be equal to root 2 GH. The same thing we are going to prove, and here this area is larger, very large as compared to this one. So here one thing will happen. If you apply equation of continuity, so A2 times V2 must be equal to A1 times B1. Since A1 is very small and A2 is very large, so you will see that velocity V2 will be negligibly small. So that concept we will make use. So let's go from the beginning. Here some information is given. So we can see speed of efflux, Toricelli's law. The word efflux means fluid outflow. Toricelli discovered that the speed of efflux from an open tank is given by a formula identical to that of freely falling body. Do you remember what is the formula for freely falling body? If you remember the relation, if body falls from height h, here suppose u is equal to 0, so at this point, what would be the velocity? So if you apply formula, v square equal to u square plus 2gh, and u is 0, what do you get? V equal to square root 2gh. The same thing we will get in case of efflux flow also here. So consider a tank containing a liquid of density rho with a small hole in its side at height y1, as we have observed. Again, we are going to see that picture. The air above the liquid whose surface is at height y2 is at pressure P. From the equation of continuity, you know, A1 V1 must be equal to A2 V2. So V2 equal to A1 upon A2 times V1. Since area A2 is very large, as you have seen in the beginning, so V2 can be taken as 0, roughly equal to 0. So here it is clear, same thing that we have already discussed. So here, if the cross-sectional area of the tank A2 is much larger than that of the whole A2, that A2 is greater than A1, then we may take the fluid to be approximately at rest at the top. What does this mean? This can be understood that suppose you have a tank filled with water, right? It contains water up to here, right? And you just make a pinhole, small hole by inserting a pin, then liquid will start coming out with velocity v. And if you observe the level at the top at which it is going down, so you will see that this level is not moving. It is almost move nothing. So that is why the same assumption is made here. It will move, but it will take days to empty the tank. So that is why in our assumption it is taken that V2 is almost 0. If V2 is 0, then from Bernoulli theorem, here if you observe the levels, so here up to here it is y1, up to here it is y2. So difference in this is the height of this hole is y1 and up to here it is y2. So this water above this hole is h, which is y2 minus y1, right? So here we are going to apply Bernoulli's theorem, and applying the Bernoulli's equation at point 1 and 2, and noting that at the hole pressure is here, if you see this is open end, so pressure will be equal to that of atmospheric pressure, and here if it is closed then pressure will be P. If it is also open, in that case P2 will be just PA, right? Now, so P1 is PA, the atmospheric pressure we have from, so we write PA equal to 1 by 2 rho V1 square plus rho G H1. H1 means height Y, we are considering this point, and then for that also we have to apply the same formula. So P times half rho V2, we have assumed that it is almost 0 and the height is Y2. Now we take this Y2 minus Y1 equal to H, as we have seen. So we will get V1. So if you evaluate V1 from here, so take this PA term to RHS, right? And also this term to RHS, and then simplify. So you will get V1 equal to 2GH, right? Here H equal to Y2 minus Y1 and plus 2P minus PA divided by rho. Now, as I told you, here if this term is closed, then pressure will be different. But suppose this end is also open, then here pressure P2 will also be equal to PA, means equal to atmospheric pressure. So in this equation, this term will become 0. When P is greater than PA, and 2GH may be ignored, the speed of efflux is determined by the container pressure. There may be two cases. When this is very high, in that case this term will be negligibly small, but if it is open, means tank is open, so in that case P and PA will be equal, then this term will vanish. So both things are given here. Such a situation occurs in rocket propulsion. The first one, when 2GS may be ignored, so that situation occurs in rocket propulsion. But in general, if the tank is open to the atmosphere, then P will be PA, and hence we will get this. So our concern was not that of rocket propulsion. Our concern was to find general situation in case of tank or any other thing. So where small hole is there and it contains a liquid, in that case what will be its rate of flow of velocity, or what will be its velocity, right? So I think you have understood. Now dynamic lift. Dynamic lift means what? So we are going to see different type of motion, means pressure difference when object moves. If velocity is higher in one side than the other, in that case what will happen? Suppose we consider a ball, and if I say here velocity is V1 and here velocity is say V2, right? If V1 is greater than V2, then what will happen? So if we apply Bernoulli theorem, so 1 by 2 rho, and we are assuming that flow is like this, or let's write all term. So general, so rho 1 V1 velocity, here rho will be taken as rho V1 square plus P1 plus rho G H1 equal to 1 by 2 rho V2 square plus P2 plus rho G H2. And we assume that H1 and H2 are same. So this term will not be there. So in that case, pressure difference we can find. So 1 by 2 rho 1 V1 square minus 1 by 2 rho 2 V2 square is equal to P2 minus P1, right? And if V1 is more, then what will happen? The pressure difference will be less in that case, because see, velocity is higher, so all three energies will sum up to a constant. So if any one is higher, then another must be lower. If general equation, if we write pressure energy plus kinetic energy plus potential energy, and we say that one energy is increasing, pressure energy plus say kinetic energy plus equal to constant, right? So if it is constant and one energy is increasing, suppose this is increasing, so another will decrease. If flow is parallel, this term will not be there, then this will decrease. If pressure will decrease, then what will happen? There will be, and suppose here pressure is less, then there will be a force upward to that direction. Wherever pressure will be less, so there will be a force to that side. So that thing we are discussing here. So ball moving without spin, if it is going normal, then nothing happens. So figure 9.11a. So first let's see figure, and after that let's analyze what they want to say. Here in this case nothing is happening, there is no velocity difference, right? Here there is spinning ball, there will be velocity difference. Here this is foil, airfoil, here also there will be velocity difference because of the shape, right? So that is what we are analyzing here. If velocity will be more, in that case pressure will be less, then there will be an upward lift. So that we are going to analyze. So let's read it. So figure shows, first of all, shows the streamline around a non-spinning ball moving relative to fluid. From the symmetry of the streamlines, it is clear that the velocity of the fluid above and below the ball at corresponding points in the same, resulting in zero pressure difference. So there won't be pressure difference if ball is not spinning. But if ball is spinning, in that case there will be a pressure difference. A ball which is spinning drags air along with it. If the surface is rough, more air will be dragged. This shows that streamlines of the air for a ball which is moving and spinning at the same time. The ball is moving forward, and relative to it, the air is moving backward. Therefore, the velocity of the air above the ball relative to the ball is larger, and below it is smaller. The streamlines thus get crowded above and rarefied below. The difference in the velocities of air results in the pressure difference between the lower and upper faces, and there is a net upward force. As I told you, wherever pressure will be less, in that case there will be force. This is called dynamic lift. So in the second case, you have seen here there is dynamic lift upward, since pressure will be less, since velocity will be more, so pressure will be less to that side, right? So there will be upward lift. Here the third one is also explained in the description. Here one more important point, Magnus effect. The difference in the velocities of air results in the pressure difference between the lower and upper faces, and there is a net upward force on the ball. This dynamic lift due to spinning is called Magnus effect, as you have seen. So on one side of the ball velocity will be less, and on other side velocity will be more. Hence there will be pressure difference, and that will cause upward lift, and this effect is called Magnus effect. So you have to reread it, try to understand. Then aerofoil or lift on aircraft wing, same thing happens. So this is designed in such a way that a pressure difference should be created, and due to that there should be an upward lift. So that you can study. Now here there is one question for you. The question says, a fully loaded Boeing aircraft has a mass of this much, 3.3 into 10 power 5 kg. Its total wing area is 500 meters square. It is in level flight. It means what is happening? Here H1 and H2. both will be same. So in Bernoulli's equation, the term containing H will not be there. Only two terms will be there. The one with kinetic energy, another with potential energy. Now estimate the pressure difference between the lower and upper faces of the wings. So force and area that we will write. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. Density of air is given. So question is simple. Let's analyze it. The weight of the Boeing aircraft is balanced by the upward force due to the pressure difference. So in question it is given that mass is this much and the velocity is this much, area is this much. So let's write force. Force will be from here mass into G. So and that will also be equal to pressure into area. So we can write delta P times A equal to 3.3 into 10 power 5. This is mass into G 9.8. So delta P equal to, since area is given as 500 meters square, so we can divide it. So we will get what is pressure difference. So the first part of the question was related to pressure difference we have found. Then in second case, this pressure difference, the force that will cause the pressure difference. So here we ignore the small height difference, as I told you, since there is level flight. So the pressure difference between them is then given by, so we can write delta P equal to rho by 2 V2 square minus V1 square. I think you have understood. This is from the fact that P1 plus half rho V1 square equal to P2 plus half rho V2 square. So from here we get P1 minus P2 we can shift, and that we can write delta P and then rho by 2 and then V2 square minus V1 square, where V2 is the speed of the air over the upper surface and V1 is the speed under the bottom surface. So here we can factorize it. V2 square minus V1 square can be written as V2 minus V1 and V2 plus V1. So V2 minus V1 we have to find out. So V2 minus V1 equal to twice of delta P, this thing. So twice of delta P divided by rho times V2 plus V1. Here V2 plus V1 divided by 2 can be taken as average speed, isn't it? So in that case we can evaluate it, and in our question average speed is given. If you observe it carefully, so here with a speed of 960 km per hour, we can take it as average speed, and we have got the relation. So here 960 V average equal to V2 plus V1 divided by 2. So this comes out to be 267 meter per second. You know how to convert kilometer per hour into meter per second. So we can put the values V2 minus V1 divided by V average. V average we have taken from there to that side. So we get this value. The speed above the wing needs to be only 8% higher than that, the below. I think you have understood. Let's re-explain. So what is happening? We are given a fully loaded Boeing B1 aircraft, 3.3 to 10 power 5 kg. Total wing area is given, and level flight with a speed of 960 km per hour, right? So we can assume this as average speed, and you know average speed V average equal to V2 plus V1 divided by 2 in meter per second we can evaluate. So this is one relation, and then there is another relation. Our concern is fractional increase in speed, right? So fractional increase in speed means V2 minus V1 divided by average speed. So that is why we have found here V2 minus V1. The relation is simple. Level flight is there, so H2 and H1 both will be same. So they will get cancelled out. So from Bernoulli theorem we will get this relation. We factorize this, and on factorization we will get V2 plus V1 and V2 minus V1, and V2 plus V1 divided by 2 can be taken as average speed. So we will get this relation, and our concern is we can write V2 plus V1 divided by 2 below it. So what would be left? So here we will get V2 minus V1 divided by V average, right? V average means this 2 and this V2 plus V1, these two terms will go to LHS, then delta P upon rho will be left, and that is to be evaluated. But one more thing, if we want to write here V average, then we have to multiply and divide it also, no? So that thing you have to take care. Like we have V2 minus V1 equal to 2 delta P divided by rho times V2 plus V1, right? This relation we can write V2 minus V1 equal to delta P rho times V average. And what do we need? We need V2 minus V1 divided by V average. So for that purpose, we have to divide both sides, LHS and RHS, by V average. So we will get delta P rho times V average whole square, right? So this we want to evaluate, and the value of delta P we have found, rho we know, and V average also we know. So after putting the values, we will get this answer. So I think now thing is clear. Further, next point is viscosity. Viscosity means thickness of liquid. So most of fluids are not ideal ones and offer some resistance to motion. This resistance to fluid motion is like an internal friction analogous to friction when a solid moves on a surface. It is called viscosity. This force exists when there is a relative motion between layers of the liquid. Suppose we consider a fluid like oil enclosed between two glass plates as shown in the figure. So let's see where the figure. So here, this is the figure. So velocity is shown, that velocity is initially V, then there is change in velocity. I think you know this concept also. Like suppose here this is shore and liquid is flowing. So here velocity will be, suppose here velocity is V, then after delta x distance velocity becomes V plus delta x. So sorry, V plus delta V means velocity is increasing. The same thing will happen from, so this is in the middle. So the highest speed will be there. So such type thing we are going to consider. So later on we will consider the term velocity gradient. When we talk about velocity gradient, what does this mean? Velocity gradient means change in velocity divided by change in distance. So delta V divided by delta x. So such thing we will consider soon. But before that, we have to just take into consideration. Here the velocity picture is shown less, than it goes on increasing. In the middle, velocity has the highest value. So that thing we are going to analyze. So let's go systematically. And keep in mind, our purpose is to make you aware with NCERT textbook. So that is why I am sticking. I can tell you other way around also as a state, but this is better to go line by line. It will be advantageous for your different type of exams. So the fluid in contact with the surface has the same velocity as that of the other surface. Hence, the layer of the liquid in contact with the top surface moves with the velocity v, and the layer of the liquid in contact with the fixed surface is stationary. So generally what happens? The layer that is in contact with, suppose the layer that is in contact with this shore, so it will have zero velocity, right? But velocity will go on increasing, and in the middle it will be highest. So same thing they are saying here. And the layer of the liquid contact with the fixed surface stationary, the velocities of layers increase uniformly from bottom zero velocity to the top layer velocity v. For any layer of liquid, its upper layer pulls it forward while lower layer pulls it backward. Of course, here what will happen? The lower layer will try to pull this layer. Here we can imagine different layers. Suppose this is one layer, there is another layer. So these layers will exert a drag. If it is moving forward, so there will be forward force. So this layer will try to pull this layer back, right? So this type of force is considered as viscous force. So here we are considering the same thing. So what happens? For any layer of liquid, its upper layer pulls it forward while lower layer pulls it backward. This results in force between layers, and this type of flow is known as laminar. The layers of liquid slide over one another as the pages of a book do when it is placed flat on a table, and a horizontal force is applied to the top cover. When a fluid is flowing in a pipe or a tube, then the velocity of the liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the walls where it becomes zero. The same thing as I told you, if you are moving toward the center, then velocity will go on increasing. Right? Now, when a fluid is flowing in a pipe or tube, then velocity of the liquid layers along the axis of the tube is maximum and decreases gradually as we move toward the walls where it becomes zero. So the velocity on a cylindrical surface in a tube is constant. So now we will consider velocity gradient and other things, and then we will try to derive the relation. So here same thing, a layer of liquid sandwiched between two parallel glass plates in which the lower plate is fixed and the upper one is moving to the right there, to the right with the velocity v. Velocity distribution for viscous flow in a pipe, as I told you, that in the middle velocity will be highest, and at the lowest, means the layer that is in contact with the wall, velocity will be almost zero. On account of this motion, a portion of liquid which at some instant has the shape ABCD, here in this figure, in the above figure, like this, they are saying that take the shape of AEFD. In the beginning it was like this, but because of fractional force it will be pushed after short interval of time. During this time interval, the liquid has undergone a shear strain of delta x by L. You have studied what is shear strain, deformation produced by original size. So since the strain in a flowing fluid increases with the time continuously, unlike a solid, here the stress is found experimentally to depend on rate of change of strain. Earlier what you have studied, it was just delta x upon L, but here it is not limited to delta x upon L because it keeps on changing, so it becomes strain rate. So delta x L delta t, or delta x upon delta t will become velocity, so we can write v upon L instead of strain rate. And the coefficient of viscosity, pronounced eta, for a fluid is defined, then we write coefficient of viscosity as eta equal to, here, force per unit area divided by strain rate. So if we arrange it, we will get F into L divided by VA. The SI unit of viscosity is Poiseuille here. Its other units are Newton second per meter square or Pascal second. The dimensions of viscosity is this much. Generally, thin liquids like water, alcohol, etc. are less viscous than thick liquids like coal tar, blood, glycerin, etc. The coefficient of viscosity for some common fluids are listed, later on you will see. And here, see the situation, there is a thin film between this mass. So what will happen? There will be a viscous drag like friction, and this is this string, here there is pulley, this is 0.01 kg mass, so definitely there will be a force due to which this will move. So let's see if some information is given about it, otherwise we will proceed to the question. A metal block of area 0.1 meter square is connected to, so this figure is related to this question, so it is simple, we can analyze it and let's see what we have to find out. So a metal block of area 0.1 meter square is connected to a 0.01 kg mass via a string that passes over an ideal pulley considered massless and frictionless as shown in the figure. A liquid with a film thickness of 0.3 mm, here thickness of the liquid film is given as 0.3 millimeter, is placed between the block and the table. When released, the block moves to the right with a constant speed. So this will move with a speed. Here there will be force downward that will pull. So there will be tension also that we can consider. So here we can apply the concept of connected motion, right? When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the fluid. We have just defined the coefficient of viscosity here like FLVA. So what all we need? We need force, we need length, we need velocity, we need area, right? So let's see whether all information is given in the question. If yes, we can easily proceed. So here the metal block moves to the right because of the tension in the string. If you remember, as we have already studied, that suppose there is one block, here there is one pulley system. So, and if there is some friction, suppose mu, although friction here we will consider another thing, but I'm just telling you, for example, and suppose there is mass M, so there will be tension T, there will be tension T, so this will move, right? So tension will cause the motion in it, and here mg minus tension will cause motion in it, and common acceleration will be there for this also. So if we write the equation of motion for this, so we can write T minus friction, which is mu times mu mg, we will take later on, equal to mass moved ma. So this is first equation for this, and here equation will be mg, here mass will be different. Suppose we write here m1 and take it m2. So in this case we will write m2g minus t will be m2a. So these are the two equations if friction coefficient is given, but here this much is not to be applied, but only we have to consider that what force is acting on it to pull it, and what force is acting here. So let's see. So force is mg, mass is given 0.10 kg, and g is 9.8. So this much force is acting, and the same force is pulling that body which is lying on the which is lying horizontally, right? So shear strain on the fluid, as we have seen, force upon area. So force we have got, area is given, so we put the value. So we then strain rate, because if you remember, we have to use shear stress divided by strain rate to get the coefficient of viscosity. So this much. Now here H, stress upon strain rate. So what is that? This is not H, they should write here eta, because purpose was something else. Here if you see what is written here, it is eta equal to F upon A divided by V upon E. Same thing we are trying to find there. So here there is misprint in the textbook. So it should have been eta equal to stress divided by strain rate, and we evaluate it, and that comes out to be 3.46 into 10 power minus 3 Pascal. I think you have understood. Now we are going to see what is Stokes' law. So Stokes' law means whenever any object, suppose we consider a spherical object, and there is a liquid here, right? So if any object falls in it, then there will be a viscous drag, there will be a force due to liquid, and its velocity will decrease. And so how, suppose its velocity is v, we assume it uniform. So if its velocity is v, then what viscous drag will act on it? So that will be equal to 6 pi eta rb, where eta will be viscosity of the liquid and r is the radius of this ball, spherical object, and the v is the velocity with which it is moving inside. Right, so we assume that velocity is uniform, not changing. So here it will move with v inside. So net viscous drag will be like this. So with the help of this, we will derive another important relation, and that will be called terminal velocity, right? So what is terminal velocity? Means, suppose we consider this ball, and it has entered in a liquid. In that case, what are the different forces that will act on it? So suppose there will be viscous drag, as we have studied, 6 pi eta rv. Also there will be another force, that is upward thrust, right? So two forces will act upward and its weight will act downward. What is upthrust force? Upward thrust or upthrust, what will be its value? How will you find out? So this force can be found by using formula volume of liquid displaced, right? So not by that, I'm going to tell you it in detail what happens. So if you remember, you have studied Archimedes principle. According to Archimedes principle, whenever any substance or any, say, body is immersed in a liquid partially or completely, then it will lose its weight, and this loss in weight is equal to the weight of liquid displaced by it. What does this mean? So let's understand it in simple way. Suppose there is a trough and that contains some liquid, right? And we lower a ball in it, right? Then, and this is filled up to the brim. When this ball is lowered, then liquid will spill. Suppose we write another container here in which liquid is occupied. This ball goes till here, then certain amount of liquid will flow and that will be collected here. Now, suppose initially weight of the ball is W1. Since it is being lowered in a liquid, it will lose its weight. So suppose new weight lost is, say, X, right? So this X will be equal to weight of the liquid displaced. Whatever liquid is displaced by it, if you find the weight of this liquid, so that will also be X. Suppose this ball was 250 gram and weight of the liquid displaced is, say, 20 gram. It means inside the liquid, the weight of this ball will be 230 gram, right? So this is Archimedes principle. The same concept we are going to make use. And suppose we want to find out what is the weight of the liquid displaced. So how will you proceed? So for that, here volume, we will consider volume of the ball, right? Then volume of the ball will displace certain liquid, and then mass equal to, what is formula? Mass equal to volume into density, right? So volume you have found and density of liquid you have to multiply, because this is liquid. Although liquid displaced will be equal to volume of the substance that is lowered in it, and then we, since this is liquid, so we have to consider its density. So this is how we will use. So we are going to derive the relation. There we will make use of these things. So our concern is to get expression for terminal velocity. So what is terminal velocity and what is its expression? So let's see what happens and how its graph will look like. So terminal velocity, as I told you, that this is object. So two forces will act on it. One will be viscous drag, and another will be upthrust. right? Now its weight will be mg downward. So viscous drag, when these three forces will be in equilibrium, then body will move with a constant velocity, and that is called terminal velocity. The same thing we are going to make use here. So viscous drag, we can say 6 pi eta, sorry, it is 6 pi eta rv. This is viscous drag. Upthrust, upthrust means volume of substance. So this volume is suppose 4 by 3 pi r cube, being spherical. Volume into density of liquid in which it is lowered. Suppose density of liquid is say rho, and then so this is mass into g. Mass into g will become weight, which is equal to force. So this is one force, this is another force, and third, it's a weight. Weight again, mass 4 into g. So m for this sphere, so its volume 4 by 3 pi r cube into its density. Suppose its density is sigma, right, into acceleration due to gravity. Our concern is to get the value of v. Now it is simple. You can keep 6 pi eta rv to in LHS and take this to RHS, then simplify. So after simplification, what do you get? So here now I am taking directly because we have analyzed. The same thing is written here. After simplification, it will become like this: V terminal equal to 2a square rho minus sigma divided by g divided by 9 eta, right? But here keep in mind this bracketed term, this density. If you have to assume the density of metal surface that is falling is more, right? So as I have told you, so that relation you will use, you will get this finally. And now on the basis of that formula, means we are going to make use of that formula to solve one question. The question is, the terminal velocity of a copper ball of radius 2 millimeter falling through a tank of oil at 20 degrees centigrade is 6.5 centimeter per second. Here terminal velocity is given, the radius of the ball is given, right? Compute the viscosity, eta is to be found, density of oil is given, density of copper is given, right? So it is simple question. We can put the values in the formula. So eta equal to 2 by 9, and then we write the difference here. It is 2 into 10 power minus 3, and it's 9.8, rho is 8.9, and velocity is given, and here density of that oil in which it is falling, that is also given. So after putting those values, we will get eta equal to this. That you can do. I think you have understood. Now there is another concept, surface tension. So free surface of any liquid behaves like a stretched membrane. So from there the concept of surface tension comes. So here sap and water rises up to the top of the leaves of the tree. Hair of a paintbrush do not cling together when dry and even when dipped in water, but form a fine tip when taken out of it. So these are certain phenomena that we observe due to the concept of surface tension, right? So we will consider here surface energy, and we will define surface tension. So mathematical expression surface tension will be force per unit length. Surface tension, and numerically surface energy will also be equal to surface tension. So there is theory that you can read. Here some pictures are given. Let's see them. Like this sphere of influence is created here, free surface. So these all particles are pulling. These particles are pulling like this. So that is why this will be have like a stretched membrane, and there will be, the concept of adhesive and cohesive forces. Like molecules, means molecules of same material attract each other, that is called force of cohesion, and force between different type of molecules is called adhesion. That is why glue stick etc are called adhesive. This is the logic behind it. You can observe them carefully, and you can find the concept behind. So here they are evaluating that suppose this is a thin film, and we are stretching it by certain distance, then there will be some work done, means area will increase. So finally we will get surface tension F upon 2L. If there will be two free surfaces, suppose this is soap film, so there will be two free surfaces. So that is why the term 2, the number 2 will be inserted. So we get S equal to F upon 12. Just go through it because this is simple definition, so I am not going in detail. There are certain uses and other things. That is your work. You will read them. And now we are going to study about angle of contact. So angle of contact you can see from here. Like in this case, this angle liquid and free surface, this angle is acute, here this angle is obtuse. So those liquids that form acute angle of contact, they stick to the surface of the material, or they wet the surface, whereas those liquids that make angle of contact obtuse, they don't wet the surface. Like mercury, this is case of mercury, this can be the case of water or any other substance or any other liquid that wets, right? So we will see some relations on the base of this, and the surface tension is also responsible for the phenomena like the spherical bodies. The drops are spherical because the sphere has the least surface area, so they try to minimize the surface area, and hence they are spherical. Now there is another concept, pressure difference inside the soap bubble, and suppose an air bubble is inside the liquid. So different type situations are there, although their derivations are not given here. So we can directly consider the results. Here two relations are given. One is bubble differs from a drop and cavity. In this case, applying the above argument, we have for a bubble, the relation is 4 times surface tension divided by radius, and in case of liquid drop, it is 2 times surface tension divided by radius. So that concept you have to memorize. Then comes capillary rise. Capillary rise means if liquid is filled and there is a fine tube, fine bore, then liquid will rise. And for this, we can derive the relation. We consider this meniscus. You understand meniscus? Meniscus means shape of the free surface. Suppose here, if you consider, if you fill a liquid, so if you fill water, so this will be like this, right? So here angle of contact will be theta. Angle theta is acute, right? So it means water will wet the surface. Now if we take this is suppose silver glass, AG glass, and we fill water, then angle of contact will be 90 degree, right? And if we fill mercury here, then the shape or meniscus will be like this. In that case, angle of contact will be, theta will be obtuse. Theta is obtuse, right? So three types of meniscus are possible. So here we are considering this type of concave meniscus, and this rising of liquid can be derived by formula. Let's see if something is given, otherwise I will derive. One consequence of the pressure difference across a curved liquid air interface here, and here there will be pressure difference, right? So what you say, pressure upside will be larger than pressure inside. That is why this type meniscus is there. But in this case, what happens if we consider 2 points? So inside pressure will be larger than outside. So this type meniscus is there. So here our concern is till this concave meniscus. To see this, consider a vertical capillary tube of circular cross section, radius A, this one. Now, inserted into an open vessel of water, the contact angle between water and glass is acute. Thus, the surface of water in the capillary is concave, as I told you. Now, this means that there is a pressure difference between the two sides of the top surface. This is given by P1 minus P2, as we have seen for a liquid drop. Pressure difference is given by 2S upon R. So 2S upon R, radius we can, from the previous figure we can check it. So it will be A sec theta or A upon cos theta. Here you can observe, here if you take this theta and this as A, so A upon R base upon hypotenuse. So that will be cos theta. So from there we can get R, this R, right? The situation is like this. If there is confusion, so I'm telling you. So situation is like this. This is R, right? This is A. So here this angle is theta. You have to relate these two. Assume this is 90 degree. So A upon R equal to cos theta. But our concern is to get R. So R equal to A upon cos theta or A sec theta, right? And as you have seen, pressure difference delta P for liquid drop is 2S upon R. In place of R, you are going to write A sec theta, and then you are going to evaluate. The same thing we were doing here. So we write as Pi minus P0 is equal to 2S upon R or 2S upon A sec theta or 2S upon A, and then denominator here sec theta, 1 upon sec theta will become cos theta. Thus the pressure of the water inside the tube just at the meniscus air water interface is less than the atmospheric pressure, right? You have seen the picture. So they are talking about this situation, this type meniscus. Here one point is taken, another point is taken here. So in here upside, since pressure is higher, that is why this is carbon meniscus, means concave meniscus. So the same thing they are stating here. Thus the pressure of the water inside the tube just at the meniscus air water interface is less than the atmospheric pressure. Consider the 2 points A and B in figure. They must be at the same pressure, namely. So now we are considering 2 points A and B in previous figure. So they will be at same pressure. Let's see that. Here. So we can consider points here, here, and if they are at same pressure. So in that case, what happens? they must be at the same pressure. So pressure P0, that point, and then above it there is liquid of a height h. So total pressure will be rho hg. So that will be pressure at IRPA, where rho is the density of the water and h is height of the capillary rise. Right. So in this formula, pressure difference we can find from here, PA minus P0 we can take, right? Because here in our question we have got PI minus P0. This we can say this is PA minus P0. We are getting the value and we will equate it. So we will get this equal to H rho g. Our basic concern was to equate the two. So when we equate, we will get this relation H rho g equal to 2s cos theta upon A, or H equal to 2s divided by rho g, right? And if we take some typical values, like if A equal to 0.05 centimeter and the surface tension of water, that will be given. So we can use this much value, and the density of water and the radius we have considered here. So after that we will get this height water rises up to, so that is 2.98 centimeters. So notice that if the liquid meniscus is convex, then what will happen? In this formula, height will be h equal to 2s rho ga. If you consider this thing, so if theta in that case will be obtuse, when theta will be obtuse, then what will happen? Cos theta at obtuse angle, what happens? It becomes negative. So liquid will fall. That happens in case of mercury. So that thing we will study later. And there is one question. Let's analyze the question and then chapter will be over. The lower end of a capillary tube of diameter 2 millimeter is dipped to 8 cm below the surface of water in beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in water? The surface tension of water at temperature of the experiment is 7.3 into 10 power minus 2 Newton per meter. 1 atmospheric pressure is this much, density of water is this much, G is this much, and also calculate the excess pressure. So question is simple, we can easily do. So as you have seen, in case of the excess pressure in a bubble of a gas in a liquid is given by 2s by r, where s is the surface tension of the liquid, and you should note that there is only one liquid surface. When there are two surfaces, in that case we will change it. It will become 4s. Right. So every information is given. We can find the pressure. The pressure outside the bubble is P0 equals to atmospheric pressure plus the pressure due to 8 cm of the water column. So atmospheric pressure is this much, that you know, and then rho gh will be the pressure due to water column. So just evaluate it. So you have got this value. Then we have to find out pressure inside. So that will be P0, this pressure, and then excess pressure formula you have to apply. So 2 times surface tension divided by radius. You can put the values, all information are given there. So you will reach here 1.02 into 10 power 5 Pascal, where the radius of the bubble is taken to be equal to the radius of the capillary tube. Since the bubble is hemispherical, we have assumed it. The answer has been rounded up to 3 significant figures. The excess pressure in the bubble is 146 Pascal. So that is our answer, and I think lesson is over. Here some basic points are there. We can read it together. The basic property of a fluid is that it can flow. The fluid does not have any resistance to change of its shape. Thus, the shape of a fluid is governed by the shape of its container. A liquid is incompressible and has a free surface of its own. A gas is compressible and it expands to occupy all the space available to it. If F is normal force exerted by the fluid, then pressure is given by force upon area, and there are some more points like unit of pressure in the Pascal, 1 atm, 1 bar, 1 torr, 1 mm of mercury. You should try to remember them. Pascal's law, you know that when pressure is applied at one point, then it is equally diminished, equally distributed or equally transmitted to every point without any loss. So a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and the walls of the containing pressure. The pressure in a fluid varies with depth, and that is given by P equal to PA, where PA is atmospheric pressure and this is pressure due to liquid column. Then there is another formula, that is equation of continuity, which is based on mass conservation, AV equal to constant. Then comes Bernoulli theorem, in which sum of three energies remains constant. And after that we studied the flux velocity, that is root 2gh, and another was Stokes law, in which we found viscous drag, which is equal to 6 pi eta RV, and after that we arrived at the terminal velocity, then surface tension and surface energy. So there are certain points to be considered by you, so you have to read them. And now in next lecture we will study about questions, numericals and theory based. Thank you for watching. Team Educate.